Hi everyone, here are your notes for chapter 21. Now we're going to get into types of error, power of a hypothesis test. So we make decisions based on a probability, but what if, we are wrong? That never happens, right? No, it does happen. So when we perform a hypothesis test, we have the following results that can happen. We could reject or fail to reject a null hypothesis, right? That's what we do when we make a decision. But in real life, two things could actually be true about two things could happen about my null hypothesis. My null hypothesis could be true, or my null hypothesis could be false. If we end up rejecting a null hypothesis that happened to be false, that's a good thing, right? Or if we end up failing to reject a null hypothesis where my null hypothesis is true, that's also a good thing. So this is where our errors come into play. What if we reject the null hypothesis, but the null hypothesis was true? Well, we just committed a type 1 error, which is otherwise known as alpha. And yes, that is the same alpha as our significance level. We call this a false positive. The other type of error we can create is a type 2 error, which is when you fail to reject the null hypothesis and your null hypothesis was actually false. Okay, so we are failing to reject something that we should have rejected, if that makes any sense, right? So we got a null hypothesis is true, a null hypothesis is false. If we end up rejecting it, then we have a type 1. If we end up failing to reject a false, then we have a type 2. So here are a little bit of, and we use beta to represent our type 1 error or type 2 error probability. So type 2 is a false negative. So here are some memes here to kind of help you out. Type 1 error, false positive, you're pregnant, congratulations. Clearly not pregnant. Type 2, false negative, you're not pregnant, when clearly you are pregnant. Here's another one, type 1 error, refs say foul, false positive, right? Type 2, false negative, no foul here. Well, I was wrong in that statement, right? So it's a false negative. Type 1 error, there is a wolf. Type 2 error, there is no wolf. A lot of students like this one because the type 1 error is the first error that the boy does in the story. He says that there is a wolf, but there is none. And then you just got to flip it for the type 2. There is no wolf, but there is one. All right, so let's go through a few situations here. So consider a test for a serious disease. What are your hypotheses? You do not have the disease. You do have the disease. So a type 1 error, a false positive. You are told that you have the disease, but you do not have it. The consequence of that, you go through unnecessary treatment and have unnecessary emotional stress. A type 2 error, you are told that you do not have the disease when you actually do. So a false negative. What's the consequence? You do not get the necessary treatment. Here's a second example. Lay's Chip Company tests a sample of potatoes from a truckload for E. coli to determine whether or not to accept the truckload. So my null hypothesis is the potatoes are good. My alternative is the potatoes have E. coli. So type 1 error, false positive. The potatoes are claimed to have E. coli, but they do not. Type 2 error, false negative. The potatoes are said to not have E. coli, but they do. So which error is worse? Which error is more concerning? So if you're the potato farmer, you're probably worried more about the type 1 error because you have a whole good batch of potatoes, but they're rejecting it, so you lose all that money. If you were the CEO of Lay's Chip Company, you're probably more concerned with a type 2 error because a lot of money would go into a lawsuit of you selling potato chips with E. coli. If you're the person buying the potato chips, probably again concerned with type 2 error. You would not really care about the type 1 error and the farmer losing out on the purchase of those potatoes. Okay, so when we think about our probability of getting a type 1 error, so whatever we put our alpha level at, that is our probability of getting a type 1 error. So if we decrease that alpha, then we're going to increase the probability of getting a type 2 error. And if we were to, so lots of times students, when we talk about alpha, they're like, why don't you just make it 1%? Well, if we make it 1%, then I have a higher chance of failing to reject a null hypothesis when I should have rejected it, right? Because what if I end up with a p-value of 0.02? Well, if I have my alpha at 0.01, I failed to reject it, but maybe that null hypothesis was actually false and I should have rejected it. And then it works the other way around too. So if we decrease the probability of type 1 error, then the probability of getting a type 1 error increases by default. So here's a good diagram that kind of represents all of this going on. So if you can see here in the blue, we have our innocent suspects, and we would hope that they would get a not guilty verdict, right? But there are some, right here in purple, that are innocent, but they end up getting a guilty verdict. So we have to think about, is that a false positive or is that a false negative? Well, that's a false positive. So that purple area right there represents your alpha, your type 1 error. And then in the dark blue, we have our smart criminals with top-notch lawyers. We hope most of them would end up getting a guilty verdict, but there would be some that don't, and that represents that yellow area, which is our beta, okay? So our type 2 error, which is our false negative. So they falsely got a negative. So they said not guilty, falsely, right? So that's a false negative. They should have had it be guilty. So you can kind of see, if you could envision, if I were to slide this bar over this direction and keep making my beta smaller, do you see how your alpha would get larger? And then the same way around. If I kept making my alpha smaller, then my beta would get larger. They're not like perfectly like 1 minus whatever, but they have that relationship that where if you make one smaller, the other one's going to get larger. So you kind of have to decide as a statistician, where is that best balance going to be? So here we have a school district is considering purchasing laptops for all high school students in hopes that using the devices will improve achievement on end-of-year exams. So what would be your hypotheses? Well, my null hypothesis would be student achievement stays the same, does not improve. My alternative would be student achievement does improve. So would this one be a one-tailed or a two-tailed test? Let's do a little bit of review from last chapter. So we're looking to see that it improves, which means we would do an upper tail, right? So a one-tailed test. So again, the district wants to show an improvement in achievement. They're not going to test for just a change in achievement because this wouldn't buy laptops if achievement got worse, because they wouldn't buy them, right? So what would be a type 1 error? So false positive. The district decides that laptops do improve achievement when they actually don't. A type 2 error. The district decides that laptops don't change student achievement when they actually do. So a false negative. What will be the consequence of a type 1? Well, the district continues to spend money on laptops that aren't actually helping students. The consequence of a type 2 error would be future students don't get access to laptops that would actually help them be more successful. So you need to decide which is a worse error, type 1 or type 2. Okay, so let's go ahead and think about our criminal trial again. So let's pretend we had a defendant that we know is guilty of a crime. So my null hypothesis is the defendant is innocent. My alternative is the defendant is guilty. What do we need in order to convict the criminal? In other words, to reject the null hypothesis. We need strong evidence, right? So that's what the whole purpose of a trial is. And we need to do it without that strong evidence, we risk committing a type 2 error, right? Because our type 2 error is a false negative. So the criminals that actually are guilty end up being told that they're not guilty, right? So, or what if we developed a new medication that I know is better than the previous one? What do I need if I want to prove that the new medication is better? Strong proof, right? Or what if we developed a new medication that I know is better than the previous one? What do I need to prove? Strong evidence, right? So I need strong evidence to prove that it is better than the previous one. So in hypothesis testing, that evidence or proof we need is called power. Bring on the power. Okay, so what is power? Power is the probability of rejecting a null hypothesis given that the null hypothesis is false, which is exactly what we hope to do, right? So AKA the probability of concluding your HA is true given that the HA is true, right? So the probability of rejecting a null hypothesis is false, or otherwise saying that my alternate is true given that it's true, right? So your power is whatever 1 minus beta is. So 1 minus the probability of your type 2 error. So if we go back to this table, right there is our power. Okay, so we reject the null hypothesis, and our null hypothesis was actually false. That's ultimately what we want to do, right? Because down here in this land, if we fail to reject our null hypothesis, we're not quite saying that it's true. But if we reject it and our null hypothesis is false, that's our power. Okay, so when we have a HA that we know is true but still need the hypothesis test to prove it's true, we need power to be as big as it can possibly be. So here are 3 ways to increase power, and you want to make sure you know all of these. You can either increase your alpha, right? Because remember, increasing your alpha decreases your beta, and power comes from 1 minus beta. But problem with this is it will also increase our probability of type 1 ideal. So that might not always be the most ideal situation for increasing our power. Second, we could increase our sample size, right? And increasing sample size is a good thing no matter what. It decreases variability between our samples. So increasing sample size will lower both the probability of type 1 and the probability of type 2, which then also increases our power. But taking a bigger sample size is not always possible or realistic. And the third one, this one's more for the people making whatever we're looking at, increase the effect size. So pretty much what this means is if you make a new thing really better by a lot, it makes it a little bit easier to see a statistically significant difference between the two things. So like if I wanted to create a medication that does weight loss, like a weight loss pill, right? I would want to create, so my effect size is that it really makes a big difference of how much weight someone loses, comparable to just like a mediocre amount of weight loss. So if I can make that gap bigger, and it's going to make it a lot easier to reject the null hypothesis when my null hypothesis is false. Okay, so that's for like, we can't as statisticians change effect size. That's just whatever the thing that we're looking at has power, or not power, determines what the effect size is, if that makes any sense. So increasing effect size does increase power, but that's something as statisticians that we can't really do. So increasing sample size or increasing alpha are the ones that we can go to. All right, that concludes your notes.